Okay, so we have a quiz today. Like we will do on quiz days, like we've always done on quiz days, we're going to jump into new material now, then we'll break for questions. This class ends at 10:40, right? So we'll cover new material until like 10 after, maybe. And then, so if I'm still yammering on at that time, just kindly remind me that now it's time to stop and go over questions that you have on the quiz material. And then we'll take the quiz. So we're going to spend some time talking about vectors. We talked about vectors at the beginning of last semester. We just restricted ourselves to the first quadrant, but now we're going to look, we're going to allow for vectors anywhere. And we already are familiar with the fact that a vector is a quantity that has both magnitude and direction. So a vector, the magnitude of a direction, or the magnitude of a vector is just the length, how far it extends from the origin. Vectors always start at the origin. And the direction is the angle that it makes with the positive x-axis. And we have this sort of standard way to kind of denote a vector, magnitude with an angle of whatever angle that might be. If we add vectors graphically, some of this is just like repeated from the first semester of notes, so this probably looks pretty familiar, but let's say I have a vector v here and a vector w here. Graphically or visually when we add them, we say we're adding them tip to tail. So I could imagine starting at the end of v and then just drawing the w vector, sliding it up, not rotating at all, but sliding it up so that it starts at the end of v and drawing that vector. And then where it ends, that vector, that's the end point of their sum. And we could have done it either way. Here, the way it's drawn, I drew w at the end of v, but I could also have drawn v at the end of w, and it forms like this parallelogram. So vector addition is commutative. You'll end up in the same spot, regardless of the order. When you multiply a vector by a scalar, which is just like a number, it just changes the magnitude. So double a vector, you just double the length, and the angle doesn't change. The only way you can change the angle by multiplying by a scalar is if you multiply by a negative, and that just flips it over the origin, so like rotates it 180 degrees. We can find components of vectors. The x component is just the x coordinate where a vector ends. And the y component is the y coordinate where the vector ends. We find the x component by taking magnitude times cosine of theta, and the y component is magnitude times sine of theta. These are both derivable, and we did it last semester just by drawing the right triangle in the plane. Drop down a perpendicular and using SOHCAHTOA. So when we find the x and y components, we say that we are resolving the vector into its components. You might see that term come up in some of the problems that you do. So suppose we've got a vector. They give us a magnitude of 5.88 and a direction of 130 degrees. What quadrant is this in? Second quadrant. So it's like here, 130 degrees. And then we have a magnitude of 5.88. Sometimes I like to just kind of sketch it out, or at least make a mental note of what quadrant a vector is in first before I start, because it gives me a sense for what to expect. I know that I should expect the x component to be negative and the y component to be positive when we find these, when we calculate these out. So Vx magnitude times cosine theta, 5.88 times cosine of 130 degrees. Vy magnitude times sine theta, 5.88 times sine of 130 degrees. One of the reasons I like to really explicitly think of that is because one of the common types of errors we make when we're calculating things is forgetting what mode our calculator might be in. So sometimes you might be able to catch that error by realizing, oh, when I found the x component, it gave me a positive, and that's weird, and I seem to have typed everything incorrectly. So that could happen if maybe you were just in the wrong mode. I'm in radian mode right now, so I'm going to switch to degree mode. So I got negative 3.78. And 5.88 times sine of 130, positive 4.50. Questions on that example? All right. Vectors have lots of applications. We already learned last semester that a force is a vector quantity. It has magnitude and direction. So here we've got a toy wagon pulled with a force of 85 newtons exerted on a handle that makes a 20 degree angle with the horizontal. And we want to know what's the effective force for moving the wagon forward. Basically, what's the x component here? So if it makes a 20, the way I've drawn this, it kind of, this vector looks like it could be a second quadrant vector. We could treat it as a second quadrant vector, but if I just got up and walked over on the other side of the wagon, it would appear, there's no coordinate axes drawn in nature, right? So we could also treat this just as a first quadrant vector. We'll still find that x component will just tell us what's the force, how many newtons moves this forward. So if we do that, here's my best wagon. It took me like 4 tries to draw that wagon the best I could, so this is on the fly. That's as good as I can do. But we could just sort of get up and walk on the other side of the wagon, treat this as a first quadrant vector. I don't think it changes how we interpret the result at all. So we want Vx. And we know that Vx is magnitude times cosine, so 85 newtons times cosine of 20 degrees. This will give us a positive. If we wanted to think of this as more of a second quadrant vector, what we would do is find the actual angle. Like think of 20 as like the reference angle, so that would be like 160 degrees, and we get a negative x component. I get 79.87 newtons. It makes sense that some of that force, some of the 85 newtons is sort of wasted, not because you're not pulling it directly forward, right? You're kind of at an angle, so some of that's like an upward force. So we know how to find components, or we're recalling from last semester, how we find components if we're given magnitude and direction. If we want to go the other way around, if we know components and we want magnitude, if we know the components and we want magnitude, we just use Pythagoras, right? Components are like the legs of a right triangle. So we can use Pythagoras to get the magnitude. And since the components are the legs of the right triangle, that means we have opposite and adjacent. We use arctan to find the angle. Now, here's where things are a little bit different from last semester. We restricted ourselves to the first quadrant last semester. So that meant that all we needed to do was find arctan of Vy over Vx, and that was it. It would always get us our angle. But arctan will only give you an angle on the right half of the circle, and in fact, even if it's in the fourth quadrant, it doesn't give you a fourth quadrant angle. It gives you like a negative acute angle. So we have to be aware of what quadrant our vector is in. Go ahead and find that reference angle like we did last class when we were using the inverse functions to find angles. Find that reference angle, which is always in the first quadrant, and then say, okay, but I know I'm in quadrant 3, so I'm going to add this to 180. So let's find the components. Oh, and actually, hold on. A quick note here. When we find the reference angle, just a reminder, we're always plugging in positives here to the arctan to make sure that we get that first quadrant angle, which in that reference angle I'm calling alpha. Okay, so they've given us a couple of components. I'm just going to do a quick sketch. It's not going to be accurate, except I'm just going to eyeball about where this belongs. Maybe about here. I don't know. The x component should be a little bit bigger than the y component. I don't know if it comes through that way, but when we find the angle, the reference angle alpha is this acute angle as a positive number. And then we're going to use that to find theta. So this is in quadrant 4. Let's go ahead and find the magnitude. I'm using Pythagoras for that. So 4.2 squared plus 3.8 squared. 5.66, or if if these were approximate numbers, it's conventional to round to the same same accuracy as the components. So if these were approximate, you could round that to 5.7. I'm going to leave it the way it is. Now for the angle, we're going to get alpha first. So we're going to find arctan absolute by over absolute bx. Arctan of 3.8 over 4.2. When you're finding the reference angle, you should always we know we should get an angle between 0 and 90 degrees, positive. If that doesn't happen, you might have forgotten to make sure you plugged in positive numbers. So 42.1 degrees. And so our angle theta, how do we get theta? Subtract it from 360. $317.9. Great, so we found magnitude and direction. You could, since it just said find the magnitude and direction, we could just circle those as our two parts of the answer they're asking us for, or we could put them together and say our vector v is magnitude 5.66 at an angle of 317.9 degrees. How's that? We know how to go back and forth, right? This is all stuff that we've done before. We have a little extra added step when we're finding the angle because, we have to account for what quadrant it's in. On the next page, again, we're going to revisit something we learned last time, how we add vectors. The process is the same. Again, we just have to be careful about what quadrant our vector is in when we do this last step of finding the magnitude, right? So making sure we get that reference angle first and then making whatever adjustment we need to make for the quadrant that our vector is in. And everything else is pretty much the same. So we're adding, let's see, a first quadrant vector, 30 degrees, and then, what, that's a third quadrant vector, 250 degrees. Let's find our components. So magnitude times cosine. The y component is magnitude times sine. So it's 1047.89. Magnitude times sine. .605. So there's the v vector. Let's do the same thing for the w vector. Magnitude times cosine. Magnitude times sine. Negative 336.89. 36.89. And then magnitude times sine. Negative 925.60. I do a quick check to make sure that things are where they ought to be. We notice that we observed in the beginning, the first vector is in the first quadrant, and the x and y are both positive, so that makes sense. We said 250 degrees, that's in the third quadrant, and x and y are both negative, so that makes sense. What's the next thing we do? I mean, we found the components of these two vectors. What comes next? Add what? Yeah, right, so we add the two x components to get the x component of what we call the resultant vector, their sum. So 1047.89 minus 336.89. $7.11. And if we add the two y components, $605 minus 925.6 is minus 320.6. Okay. We have the components. We know where our vector ends. What comes next? Finding the angle and magnitude. Yeah, so we need magnitude and direction. What quadrant is this in? 4. Yep. So that means that when we find the angle, we're going to have to subtract a reference angle from 360. Let's go ahead and get the magnitude. 779.94. We're going to find alpha. We make sure that we always plug in positives to the arctan function to get our reference angle. So it's going to be positive y component over positive x component. So 320.6 over 711. .3 degrees. And it's in the fourth quadrant, so theta is 360 minus 24.3 degrees. .335.7. And so we wanted to find the resultant vector. They didn't just say find the magnitude and direction. So we really want to kind of put these two pieces together to say here's our resultant vector. It's got a magnitude of 779.94 at an angle of 335.7 degrees. You know, I broke out finding that angle, theta, into two pieces, right? First finding the reference angle and then saying, let's go ahead and subtract. You know, after you do a bunch of these, a lot of people might just kind of roll that into one step and say, oh, this is in quadrant 4, so I know when I find theta, I'm going to take 360 and subtract arctan of, you know, 320.6 over 711, and that's totally fine to do. Just make sure that if you do that, you're still making sure that you plug in the positives into the arctan, right? The idea is that this is the reference angle that you're using to make an adjustment based on the quadrant. Ready for more? Okay. All right. Here we've got three vectors to add. We should observe that they've only given us explicitly the angle for one of the vectors. That first quadrant vector we know is a magnitude 0.75 at an angle of 15 degrees. All the other ones, they gave us acute angles measured from some reference. So this third quadrant vector, I'll call that theta 2. This will be, I'll call this V1, V2, V3. And what is the angle for the second vector? What is theta 2? Yeah, great. So 192.4. And what about for V3?
360.
270 plus. They gave it to us from a vertical reference, right? So that's a. What's that?
I was gonna go backwards, but I saw what they gave us.
Yeah. Yeah, so we got to add to 270 there. Plus 74. What is it? 344.4. Great. All right, so here are our vectors. V1, 0.750 at 15 degrees. V2 is 0.265 at 192.4, and V3 is 0.548 at an angle of 344.4. we're going to add them up. That procedure that we use to add two vectors works no matter how many vectors. The x component of your sum of your resultant vector you just get by adding up all your x components. I could add 10 vectors. I just find all 10 x components, add up the 10 x to find rx. Find all 10 y components, add them up to get ry. So we're going to do this with 3 vectors. So we're going to have to kind of churn out some components. I'm going to kind of just make a little table here. X component, y component, v1. Let's see, so we're going to do 0.750 cosine of 15 degrees. That is 0.724. The y component 0.750 sine 15 degrees. Point 194. I'll just keep going. So 0.265, and then the angle is 192.4. And for the third vector, 0.548, and the angle is 344.4. And now we'll just kind of bang out these calculations on the calculator. 0.265 cosine 192.4. Negative 0.259. And for sine, the y component, negative 0.0569. And for the last vector, that angle is 344.4. So the x component is 0.529 or 5.528. Y component negative 0.147. It's sort of like a really algorithmic approach to this. You know, once we have our magnitude and direction for all our vectors, we find all of our components. Let's get our x. So our x, we're just going to add the x components. And if we add these up, 0.724 plus negative 0.259 plus 0.528 is 0.993. And then same for the y component. negative 0.0099. So this vector is almost all x component. It's like really close to the positive x-axis, but a little bit below it. So we're going to expect what kind of angle? Well, theta. Let's think about what theta should be. Very close to 360, right? And if we think about alpha, it's just very small, right? Pretty close to 0. So let's finish this out. Let's see what we get. So we have a magnitude 0.993 squared plus negative 0.099 squared. .99 really, I mean, pretty close to just 0.993 if I'm using 3 significant digits. It's a slightly longer, of course, because it's the hypotenuse of a really like sliver of a right triangle. So like 0.99305, all right. If we were using like 3 significant digits, we would just call it 0.993. And this is in the 4th quadrant, so theta, I'm going to take 360 and subtract the reference angle, which is given by arctan of 0.0099 over 0.993. .4 degrees. Pretty close to 360. How's that? Pretty good. I think what I'll do is actually just stop there, because we're not going to get too far through applications in 7 minutes. We'll cover applications on Tuesday, and also get a start on the next chapter on oblique triangles. And I think I mentioned this before, but the first 4 chapters is the material for our first test. So, you know, if I were to just sort of spitball, like, maybe either, I'm going to say either like the 18th or the 20th might end up being the day that we have our first test. We'll kind of see as we get closer, like how we're progressing through the material, but that's just a really rough estimate, so you can kind of just jot that down. Okay. We're going to do this next time. Questions? We're having a quiz today. We're going to go with algebraic fractions, right? So a lot of factoring and reducing. How do we multiply or divide fractions, or add and subtract, or maybe solve an equation that has fractions, least common denominator, that kind of stuff. A couple questions on that material. A couple questions on what we covered in chapter 2. So how do I find an angle? if I know what secant is or tangent or sine or something, do I know there's going to be two quadrants, right? And like how I make adjustments to get that angle. And then there was that section on applications, the arc length, the area, and angular velocity or rotational velocity. And those three formulas, which you don't have to memorize, so those will be given, but you need to be able to know what formula to use and know what things mean. I'm not going to remind you that theta, during the quiz, that theta has to be in radians for any of those formulas to work. So, don't ask. But I'm reminding you now that theta has to be in radians for any of those formulas to work. So I'll take questions that you have. Any questions on the exercises?
Can we go over the spotlight beam on the practice quiz?
Sure. I think I might actually have it. Oh yeah, okay. So in this problem, they said, a spotlight sweeps through a horizontal angle of 75 degrees. So that just means like this. Think of this as like a bird's eye view, an overhead view. Here's the spotlight, and it's just rotating. It covers 75 degrees. It can rotate through 75 degrees. And the spotlight can reach 250 feet away. So like through like a full rotation, how much area is accounted for? It can, not that it's all illuminated at the same time, but like over time it will illuminate like how much total area. So in a problem like this, I had to remember that the formulas I have are only valid if theta is in radians. So we start by converting that angle to radians. Some people approximate it. I just wrote it in terms of pi because the numbers were kind of convenient. Either way is fine. And then the formula here is theta r squared over 2. You don't have to memorize that, but you need to be able to find it on the sheet. Be like, oh, here's the one I need there. And then they gave us the radius. And so we plug in the radius. Here's our angle. And then we just calculate it. Radians, remember, are dimensionless. So we just get the units of feet squared and no radians in our answer. Does that make sense? Is there a piece of this that is either confusing or like how we interpret the information given? Or?
Would you always use 180 for rad? Because these two rad would be 360.
Oh yeah, I mean pi rad over 180 degrees or 2 pi rad over 360. Either's fine. Or pi over 2 rad for 90 degrees. It's fine. This I just think of as like a more reduced fraction. I'm abusing that vocabulary a little bit just because pi is irrational anyway, so think of that as a reduced fraction. But I got rid of the factor of 2. So I usually use pi rads equal to 180, but you could use 2 pi and 360 if you want. Other questions?
Yeah, I have a question on some of the homework.
Yep.
For using the angular velocity.
Yes.
When we're using v equals omega r, does omega have to be in rads?
Omega is always radians per unit time.
So
Yes.
they gave us revolutions, and we have to.
Then you have to
convert
use the fact that one revolution is how many radians?
And then if we calculate something using that, then it spits out radians, and then if we need revolutions, we have to convert.
Oh, you mean like if we're asked to find omega in revolutions per unit time?
Right.
Like, is there-
like 43? Question 43.
Oh yeah, that's a good one.
That was a good one. Took me a couple of tries.
Yeah. Oh, that's a really good one. Okay. So for this one, please forgive this awful drawing I'm going to do. We have a bicycle wheel, and then here's the little spoke, right? Or the little gear or whatever. Not spoke, but the little gear. And then it's attached to a little pedal gear. So here's a little pedal, and then there's a chain, right? Bicycle chain. So the whole idea behind this That's not bad.
Is that the
I've done worse. The whole idea here is that, when you're pedaling, this goes at so many revolutions, however fast I'm pedaling. And it spins this guy, and this guy's going so many revolutions per whatever, or angular velocity, maybe radians per whatever. And then that'll spin this wheel. And they give us the different radii. So they tell us that this is 5 inches. They tell us that this is 2 inches, and that this is 14 inches. And they say that we want to go 15 miles per hour. The bicycle wants to go 15 miles an hour. So if the bicycle wants to go 15 miles per hour, what that means is that the linear velocity of the wheel is 15 miles per hour. And we want to know the angular velocity here in revolutions per minute. So there's all sorts of things at play here. That's why I like this problem, because our units are a mess right now. We have a desired speed of 15 miles per hour, and we would kind of think about speeds in those units. We're not going to measure a radius in miles, obviously, right? So it's natural that we measure the radii in inches instead of miles. So the first thing I did, and we want omega in revolutions per minute, not hour. So the first thing I would do if I were working out this problem is just convert miles per hour to inches per minute, and that will kind of take care of the units. So 1 hour, 60 minutes, 1 mile, 5,280 feet. So 15 divided by 60 times 5,280, 1320 inches per minute. Oh, never mind. Hold on, I'm not done. 1 foot, 12 inches times 12. A lot. 15,840 inches per minute. Okay, so that's V, the linear velocity for the wheel. I'm going to answer the question you asked directly right now. When you're using V equals omega r to solve for omega, it is automatically in radians per, in this case, radians per minute. So then you'd have to convert that to revolutions. But I like this problem because it makes us do this in like a few steps. So I know the linear velocity for the wheel, so that means I could find the angular velocity with the knowing the radius. So V equals omega r means omega is V over r, which is 15,840 over 14, and this is 1131.43 radians per minute. Okay. The angular velocity that we just found of the wheel has to be the same as the angular velocity of this gear, right, in the wheel. So I know omega for this, which means I could find V. I could find the linear velocity for that little wheel. And that's good, because the linear velocity for the wheel is the linear velocity for the chain, and it's got to be the same as the linear velocity for the pedal gear. So this is omega for the wheel and for the wheel gear. And I'll just actually say for the chain. Or no, because that doesn't make sense. For the chain's not a circle. I'll just say wheel. Okay. So the velocity for that chain is omega times the radius of the gear. So that's 1131.43 times 2 inches. And that's 2262.86. Is the velocity of the chain, which is the linear velocity of the pedal gear. And so then we can find the angular velocity. So that's 2262.86 divided by 5 inches. 452.57, and this is in radians per minute. So then we just have to convert that to revolutions. .03, so I'll just call that 72. How's that? Kind of fun. Tracing values through the diagram. Other questions? Are we good at finding angles located anywhere in the plane? Sure? Okay. What? Yeah, but you know, there's time to ask questions. Or there's also time to not ask questions. Okay, good.